Welcome back to the weekly Tech Digest for week of July 4th, 2026. This week we cover 14 topics, including using local coding agents, OpenMontage, and omnigent-meta-harness-kubernetes, plus 11 more. Let's get into it. Setting up a local coding agent using open-source tools offers privacy, cost efficiency, and flexibility compared to proprietary alternatives. Running coding agents locally incurs only hardware and electricity costs, ensuring data privacy by avoiding third-party services. Using QN 3.6 with its dedicated harness, QN Code yields the best coding performance due to optimization for its architecture. QN can run both codecs and QN models, accommodating different coding preferences without manual switching. Local coding agents allow function in scenarios with limited or no internet connectivity, ideal for programming retreats or travel. Local setups are cost-effective and privacy-conscious, offering optimized performance and offline usability. What are your experiences with using local coding agents compared to proprietary options? OpenMontage revolutionizes video production by enabling users to create videos through natural language instructions that harness various AI tools and free resources. OpenMontage allows for true video production rather than simple image animations. It builds a video using actual motion clips sourced from free stock footage and open archives, leading to fully rendered video content. The system integrates multiple AI tools for different aspects of video production. It manages everything from research and scripting to asset generation and editing within a single pipeline. Users can start video projects from an existing reference video to expedite production. By analyzing elements of the reference video, OpenMontage generates differentiated concepts and production plans with cost estimates. The backlot feature enhances oversight during production. It provides a live view of the production process and allows users to approve assets at key stages before final rendering. Zero API keys can still create complete videos. Out of the box, OpenMontage provides access to various free resources while still enabling high-quality video production. OpenMontage empowers video creators by harnessing natural language to build videos. It integrates multiple AI tools effectively and facilitates oversight and quality control. What potential do you see for AI in creative video production? Omnigent provides a powerful abstraction layer for managing AI agents. This enhances security and policy enforcement for infrastructure engineers. It serves as a meta-harness, enabling consistent policy enforcement and session management across various agent implementations. Omnigent standardizes the management of AI agents by serving as a meta-harness. It enables uniform session management and wraps individual AI agents behind a common API, ensuring consistent policy enforcement. The architecture of Omnigent resembles established patterns in Kubernetes. Its runner, server, and database mimic the typical structure of a stateful web service that you have likely deployed before. Omnigent features policy management that is stateful and contextual. This allows policies to adapt based on prior actions, enhancing security beyond simple allow or deny lists. Choosing the right database is critical for deployment. While SQLite works for local demos, it lacks persistence in Kubernetes. Postgres, on the other hand, offers the durability and scalability needed for production environments. When deploying Omnigent, there are key considerations to keep in mind. First, understand the runner's networking requirements for effective policy enforcement. Next, you'll need to decide between SQLite and Postgres for your database configuration. In summary, standardizing AI agent management enhances efficiency, while choosing the right database can make a significant difference in deployment. Contextual policies improve security. How will you define your agent's policy rules to best manage risk in your organization? Neural architecture search enables systematic exploration of model architectures, potentially leading to higher performance and efficiency in deep learning tasks. NAS comprises three main components: search space, search algorithm, and evaluation strategy. These elements are crucial for systematically exploring architecture spaces. The NAS net search space optimizes architectures through repeated cell structures. It utilizes normal and reduction cells, significantly shrinking the overall search space while improving transferability across datasets. Hierarchical representation improves search effectiveness. These structures use primitive operations to recursively build complex network motifs, leading to enhanced architecture performance through better organization. Scheduled drop path improves performance in NAS. This technique stochastically drops architecture paths during training, enhancing robustness and the performance of the final models. In the experiments by Zoff and Lay in 2017, 800 GPUs were used for parallel processing. This setup allowed for a duration of 28 days, focused on optimizing NAS. To summarize, neural architecture search includes three critical components: the search space, algorithm, and evaluation strategy. Hierarchical structures significantly enhance operational efficiency, while scheduled drop path boosts model robustness. What novel methods could further enhance the efficiency of neural architecture search? Exploration strategies in deep reinforcement learning are crucial for optimizing agent performance in sparse or noisy environments. The hard exploration problem complicates agent learning. Agents struggle to find optimal solutions in environments with sparse rewards, often leading to local minima. Montezuma's Revenge serves as a benchmark for hard exploration challenges. The noisy TV problem depicts ineffective exploration, where an RL agent can get distracted by non-informative rewards, failing to progress toward its goals. This leads to agent behavior similar to a couch potato. Intrinsic rewards can enhance exploration by providing bonuses for novel experiences. Combining extrinsic and intrinsic rewards encourages agents to explore. The effective reward formula is R_T equals R_E_T plus beta R_I_T. Count-based exploration addresses novelty measurement by tracking the frequency of state visits. This method rewards agents for exploring less common states, with the empirical count function being a key concept. Hashing methods improve state tracking in high-dimensional spaces. Techniques such as SimHash allow for practical counting of states by discretizing them into hash codes. Utilizing locality-sensitive hashing helps overcome high-dimensional tracking challenges. To summarize, effective exploration is vital for agent performance. Intrinsic rewards can significantly boost exploration, while count-based methods help promote novelty by rewarding less common states. What are the implications of intrinsic rewards on long-term exploration strategies? Recent enhancements to transformer models significantly improve their efficiency, attention span, and suitability for a variety of tasks. The multi-head self-attention mechanism improves model performance by allowing the model to focus on different parts of the input sequence simultaneously. This captures varied contextual information, enhancing predictive accuracy. Transformer models have shown remarkable adaptability for various tasks. Different versions, such as Transformer XL and GTR-XL, optimize attention mechanisms to handle longer dependencies and reinforce training outcomes. Adaptive computation time enables dynamic computation in recurrent neural networks. This mechanism allows the model to adjust the number of computational steps based on the input, improving efficiency and speed. In transformers, the segment length is 32 in sinusoidal positional encoding. Additionally, the positional encoding dimension is 128, which plays a crucial role in the model's understanding of sequence order. In summary, transformers leverage multi-head self-attention to enhance accuracy and demonstrate remarkable adaptability across varying tasks. Additionally, dynamic computation improves efficiency in their operations. What future improvements do you think will have the most significant impact on transformer models? Curriculum learning efficiently trains reinforcement learning models by structuring tasks in a progressive manner. This method enhances learning by simplifying initial tasks and gradually introducing complexity, ultimately improving performance and training speed. Task-oriented strategies are essential as they enhance model performance. For instance, Bengio and colleagues found that cleaner examples facilitate faster generalization. Additionally, gradually increasing task complexity significantly speeds up the training process. Automatic curriculum learning optimizes the learning progression by framing it as an n-armed bandit problem, as discussed by Graves and colleagues. This approach enables adaptive policy formulation, allowing for more efficient task selection during training. Self-play frameworks further improve task learning by enabling agents to learn from each other through competition. Sukhmatar and colleagues introduced asymmetric self-play, allowing agents to engage in a competitive environment, which significantly enhances their learning experiences. Curriculum design plays a crucial role in effective training. An inefficient curriculum can severely hinder learning progress, underscoring the necessity for careful design and accurate task difficulty metrics to foster optimal learning outcomes. In summary, structured tasks enhance learning speed, while adaptive learning policies provide substantial benefits. Additionally, the efficiency of the curriculum design is crucial for achieving success. What are the key challenges in designing an effective curriculum for reinforcement learning? Self-supervised learning enables engineers to leverage vast amounts of unlabeled data by using pretext tasks to generate supervision from the data itself. Self-supervised learning provides free labels for unlabeled data. By framing supervised tasks to learn from the data itself rather than requiring manual labeling, engineers can make use of the vast amounts of unlabeled data available. Rotational prediction is a useful self-supervised task. Training a model to predict the rotation applied to an image helps it learn semantic concepts by forcing it to recognize high-level object parts. Predicting relative positions of image patches helps learn spatial context. This pretext task requires the model to understand the relationships between patches, fostering learning invariant features. Jigsaw puzzles serve as an effective self-supervised learning strategy. The task trains the model to rearrange shuffled patches, allowing it to learn context and relationships between parts. To implement self-supervised learning, define a pretext task using unlabeled data, train a model to learn representations based on that task, and finally, evaluate the learned features with a downstream task. Self-supervised learning allows for the effective use of vast amounts of unlabeled data through various pretext tasks. Consider what pretext tasks you think are most effective for self-supervised learning. Evolution strategies, or ES, provide an effective black box optimization method. They enhance the performance of deep learning, especially in environments where gradients are unavailable. This is crucial for optimizing functions without needing gradient information. CMA-ES improves upon the basic ES approach by adapting the covariance matrix. By tracking dependencies between samples, CMA-ES allows for a dynamic adjustment of the sample distribution, thereby enhancing both exploration and convergence. Natural evolution strategies utilize natural gradients for improved parameter updates. These updates penalize directions with high uncertainty, resulting in more trustworthy adjustments during the optimization process. Evolution strategies have significant applications in reinforcement learning. Notably, OpenAI has successfully employed ES to optimize reinforcement learning policies, showcasing its efficacy in complex environments. ES algorithms are adaptable for hyperparameter tuning in deep learning. Utilizing methods like population-based training, ES can enhance model performance through systematic adjustments to the hyperparameters. The simple Gaussian evolution strategies process consists of several steps. You begin by initializing parameters, then generating population samples, and evaluating their fitness. Afterward, elite samples are selected, and parameters are updated based on these elite samples. In summary, evolution strategies optimize without the need for gradient information. CMA, ES, and natural evolution strategies enhance performance significantly. They are also adaptable for applications in reinforcement learning and hyperparameter tuning. How do you see evolution strategies changing the future of optimization in AI fields? Humans should focus on managing the overall software development loop while allowing AI agents to handle the implementation details. The why loop is essential for outcomes in software development. Humans run the why loop to ensure that the work produced aligns with desired outcomes and evolving ideas. The how loop contains multiple levels of work. The outer loop delivers working software, while inner loops focus on generating and validating code. Quality of the code is less important than external outcomes. While internal quality contributes to development efficiency, the main focus should remain on functional and operational quality for end users. Shifting left improves efficiency for both humans and agents. By integrating testing and quality assessments earlier in the development process, both humans and AI agents can deliver better results. In the loop, humans inspect each line of code and directly edit artifacts. On the loop, humans focus on improving the harness for better output, while agents autonomously enhance code quality. Humans should focus on managing the software development loop while allowing AI agents to implement details. Shifting left enhances efficiency. How will the role of humans in software development evolve as AI capabilities increase? Meta-reinforcement learning, or Meta-RL, aims to develop agents that can quickly adapt to unseen tasks. This adaptability promises significant advancements in general-purpose reinforcement learning systems. Meta-RL utilizes a dual optimization loop. The outer loop adjusts parameters that govern the agent's behavior, while the inner loop focuses on maximizing reward through interactions with the environment. Incorporation of historical inputs significantly improves performance. Meta-RL models utilize the last reward and last action as inputs alongside the current state. This approach enhances the model's ability to adapt its strategy effectively. Key components of Meta-RL include memory, algorithms, and diverse tasks. A recurrent network with memory allows agents to rapidly adapt to various tasks, facilitated by a meta-learning algorithm that optimizes model weights among a wide distribution of Markov decision processes. Meta-learning can dynamically tune hyperparameters. Agents can adjust meta-parameters online, such as the discount factor and bootstrapping parameter, which improves adaptability during the training process. The training process for Meta-RL involves sampling a new Markov decision process from the task distribution, resetting the model's hidden state, collecting multiple trajectories, and updating the model weights. This process repeats to ensure effective learning. In summary, agents developed through Meta-RL can quickly adapt to new tasks, utilize historical data to improve learning efficiency, and dynamically tune hyperparameters. What implications does Meta-RL have for the future of AI development? Domain randomization significantly enhances the transferability of models from simulation to real-world applications in robotics by exposing them to a diverse set of training environments. Domain randomization creates a variety of simulated environments. By applying randomized parameters during training, the model becomes adaptable to real-world scenarios, which are represented as a specific instance within the randomized training space. Uniform domain randomization involves sampling parameters uniformly within set bounds. It allows for control over various environmental factors, from visual appearances to physical dynamics, enhancing the model's robustness. Guided domain randomization optimizes model training by leveraging performance feedback. By using real data and task performance as guides for randomization parameters, it avoids training in impractical simulated conditions and improves learning efficiency. The importance of domain variation cannot be overstated. Broader training environments enhance learning and facilitate better adaptation in real scenarios, which is key to successful robotics applications. Key takeaways on domain randomization include that randomization increases model adaptability, guided approaches improve efficiency, and varied environments lead to better outcomes. What challenges do you think remain for effective domain randomization in real-world robotics? Deep neural networks exhibit surprising generalization capability, despite their tendency for overfitting. This highlights a complex interplay between model architecture and data characteristics. Deep neural networks can learn random noise, suggesting that they have substantial flexibility. However, this also raises concerns about overfitting and model effectiveness. Regularization techniques are not the primary factor in model generalization. Understanding intrinsic dimensions and other mechanisms is crucial to grasping why deep neural networks can generalize. The concept of intrinsic dimension influences overfitting. This indicates that the effective capacity of a model to generalize is linked to the complexity of the data, rather than solely the number of parameters. The lottery ticket hypothesis suggests that not all parameters are equally necessary. There are, winning, subsets of parameters that contribute most to effective learning. For a two-layer neural network, the number of weights required is 2 times the number of samples plus the number of dimensions. This relationship is essential for understanding model design. To summarize, deep neural networks can learn noise, risking overfitting. It's important to focus on intrinsic dimensions for generalization and to balance model complexity with effective learning. Open question: how can we balance model complexity with generalization in deep learning? Kimi K 2.7 code introduces an open weight model in GitHub Copilot, providing a cost-effective and flexible option for developers. Kimi K 2.7 is the first open weight model in Copilot. Users can select it from the model picker, enhancing their coding options significantly. The model is rolling out gradually to various Copilot plans. Users in Pro, Pro Plus, and Max plans will get access first, followed by Business and Enterprise plans. Administrators must enable Kimi K 2.7 for Business and Enterprise plans. The model is off by default to allow organizations to evaluate their security and compliance requirements. In summary, Kimi K 2.7 provides flexible coding options with availability depending on the plan type. Administrators control model activation to meet security needs. How do you think the introduction of open weight models will impact coding practices in organizations? That's everything for this week's digest. Links to every post are in the description below. Drop a comment. Which topic did you find most useful this week? I'll see you next Friday.